So I became the maintainer of ASDF. I started making it robust and portable. That was ASDF2. And at the end, there was just one little bug left, and I was bored at work. And this bug has been fixed in half the cases, in the easy case, with a one-liner. There's only one bug left. It has been half fixed with a one-liner. How hard can it be? So, famous last word. So I opened the bug, and okay, and I realized, wow, the bug is not working because ASDF has never been propagating timestamps, and yet it was working. Hold on. So it was never propagating timestamps. So it was never even doing its job. And yet it was working for most people in most of the cases, but it was not doing its job at heart. So I had to rewrite it. And then I had to rewrite it again and again. And there was a guy who had written a parallelizing version of ASDF, and I had been maintaining it for whatever reason, and it didn't understand half of the code he put in. Why does it do this thing? And, like, it doesn't make sense, it's inefficient, whatever. So I removed it. And as I fixed ASDF, I noticed that, hey, everything that he added was added for a reason. He did it wrong, but he added it for a good. It was basically a bad implementation of the correct solution. And so in the end, I rewrote like ASDF 2 or 3 times, and I sunk insane amounts of work into it, and I made it portable, etc. Now you can dump very easily binaries in Common Lisp portably across like 10 or more implementations, and you can do scripting in Common Lisp. You can do hashbang user bin CL and use it as a scripting language. That's why I don't use shell scripts or Ruby or Python or Perl or anything. I use Common Lisp for all my scripting needs.
Very interesting. The two functions are equal. Seems like it'd be a nice language to use for that too. So
yeah, I mean, nicer than the other ones, but I don't think it's nice enough. But so I wrote an article about that, ASDF 3, or why Common Lisp is now an acceptable scripting language, where I describe all these things. And yeah, and actually I noticed that make is also broken for most people, because make does not propagate changes from the .h in other modules, unless you have a make depth step that computes the dependencies to .h files in other modules, which most people don't do. Make is also broken. So most projects with make are just as broken as ASDF used to be. So that was my. Oh, okay, it's broken, but actually, it's not more broken than for other languages, so that's fine.
It's just broken for everyone.
It's just broken for everyone, exactly.
So
we started.
Is that not broken?
Sorry?
If it's broken for everybody, is that by definition still broken, or is it just expected to work?
There's a thing foobar. FDAP.
Beyond all
business as
repair.
Yeah, beyond all repair.
The recognition. Huh?
It sounds more like snafu. Just there's
Snafu.
state or status normal.
Yeah, that was snafu. Yes, snafu. Yes. Status normal. All fucked up. Okay, that's snafu.
Might be both, I guess.
Yes, it's, in this case, it's snafu. But yes, what I'll argue is that a lot of a lot of software done today is snafu. I will try to explain why it's snafu. That's my talk.
Brilliant.
Tell me that after the talk.
What is non-league American?
It's soccer.
Oh, cool. Cool.
So there's like a bunch of simulators.
Cool. I was aware of that.
By the way, is there enough batteries in this?
Yeah, it's fine.
Okay.
In the U.S. compared to like a lot of other places.
Yeah, a lot of the places for sure. A lot of people continue to have college and stuff. So
That's good. That's really good. Not much of a sports person, from my understanding, since one of the better ones.
oh well, sports are
Yeah.
just a way to get aggression out.
Is it?
I don't know. You like them more if you're better at them.
Okay.
Or if you're better at one of them. So I wouldn't say that
play sports, they just watch them, I feel like.
Okay. Other questions that are not on the talks?
Are you a big soccer player, I guess? Are you in one of the semi-pro leagues?
No. It's okay to play.
Okay. Okay.
So I see you have a Lisp thing. What do you write in Lisp?
I use SBCL.
Okay.
I write, like,
What do you write with it?
it's like an automation platform for launching
For launching what?
attacks.
Attacks. Ooh. Okay. Black hat hacking. Okay. I know someone else doing that in Scheme. I know someone else doing this kind of things in Scheme.
Really?
Yeah.
Where for? Or who?
Maybe we should talk after.
That's the scheme one, right?
Which Racket?
The
Yes.
bottom right.
This is
I learned
Racket.
that in high school, which is totally like surreal to me because I kind of started with like C, C++, and then I went to Scheme and learned like a bunch of functional stuff from it. And then I went back, and then I was like, when I started relearning functional programming, I was like, this all makes so much more sense. Like, I don't know why I didn't just continue with it.
It's still time to go back to it.
Are you a big Haskell person too?
I've written maybe a few tens of lines of real Haskell.
Okay.
So, I read a lot of things about Haskell. I'm fascinated by it. Ooh, there's
amazing research papers.
Let's look more professional. Can someone help me look more professional? Yes, lectern. It gives someone authority. Oh, it's a lectern. Ooh. More so than this setup here. Well, this is not working, so go back.
That was from the functional Java, the beginning functional JavaScript talk.
Oh.
Which that was the answer to those were the practical answer to what makes a good function.
Okay. Nice. Okay. Performance.
What time is it?
It is 9:44.
9:44.
How was that one?
It was really good, actually. It was very, very heavy into Ramza as a Ramza dependency, but it taught good practices that you can use and apply with any library. So what I really liked about random is probably something that's going to affect how I program when I go back to work is treat every function as a create function.
Yeah, we put the thing that we changed at first. But that's one of the best things that Lambda did, it puts things in the right order.
Right.
Which Elixir gets wrong too.
Yeah, not just the. I mean, to be honest, some of the reverse ordering is slightly unintuitive. I mean, as long as you figure it out right, add this to that. What I might want to add with this or some other syntax, like I would expect if I would visualize it to see the first part on the left and the second part on the right. And it's reversed. But there are no curry, right? It just takes any function, makes it curry, and then if you curry that function, you can pass as many parameters as you want. Like, that's just awesome.
Oh, totally.
Yeah. I want that for like all my JavaScript functions.
We tried Haskell yet?
Yes, a year ago, for about an hour.
Get the Haskell book. You get a discount for it in your this thing.
Yeah, I think one of my takeaways from this conference is I got to go home and learn Haskell.
Yeah, I'm surprised how many people have Haskell. Like, it's shocking to me because it's not this common a language, but it seems like over 50% of the people here know it.
Because the people here want to be functional.
Oh yeah, yeah. And it's one of those languages that.
Yeah, it seems like the granddaddy of all functional languages that everything tries to model itself after.
Yeah, I can see that.
So since you're here in advance, I will show you my previous some slides from my previous talk at Boston Haskell last week, which may be relevant afterwards. So, if you consider computation as operational semantics, an operational semantics has nodes, say state A, and then it evolves to state A prime and evolves to state, and sometimes there are side effects, so here there are no side effects, and here there's some side effect. Okay? So you can think, for instance, if you want to print hello world, you start from the beginning of the program with an empty stack. You put hello world in the stack, and then you pop the stack and you print it. So that is trivial computation. Okay. Now what you want to do is, say I have some computation A, which has a set of nodes and things like that, and I have a computation C. And what does it mean for C to implement A? Well, what it means is that we have this diagram where in the black I have the hypothesis. It means that I have some correspondence between some subset of states of C to a subset of states of A. And whenever I compute something in C that has some meaning in A, I want this arrow to be there. That's what it means for this correspondence to be an implementation. Now, what are interesting properties of implementations? We can have this diagram, for instance. What does this diagram mean? So this is a property that everyone should have. It's called soundness. If you don't have that, your implementation is good to throw in the trash. Basically, it will give you wrong answers. If you have that, that doesn't guarantee that your implementation will give you an answer, but if it gives you an answer, the answer is correct. That's what that means. This thing is called totality, which means that if I have something in the abstract, I know how to implement it in the concrete. And obviously, if your abstract system is infinite, near-complete system is finite, you can't have totality. But you can have totality in most of your reasoning chain and just use it at the end because, for instance, you get out of memory, and that's fine. Something that looks like totality is that which means if I know how to compute something in the abstract, I can do it in the concrete. Which means basically this is a tracing debugger. It means I can trace my debugger and advance by exactly how much I want, and then restart the implementation or do some things. Okay. What are interesting properties? Liveness. How do I know that my implementation keeps running? That means that something like that. You start from a state that makes sense, and you have a sequence C1, C2, Cn, and you want basically that if n is big enough, you want to have this. You want to have advanced. But remember, not every state is meaningful and doesn't have to be. What you really want is this. You want that it's as if I went past something. So this is liveness. And now for the property that everyone is missing, and that I will depend on somewhere later, but I won't tell you the details later. The property that everyone is missing is this one. We start like this, A. So I'm starting a computation. And remember, the intermediate states don't have to have a meaning. For instance, when I'm doing a transaction, in the middle I'm taking, decreasing this register, I haven't increased that register yet. It's transaction. I disrupt it. What can I do? I cannot do anything. It may be holding a lock, it may be in a solid state. All I can do is wait and at some point resume it. That's all you can do. That's why, for instance, in Java or C++ or whatever, you cannot kill a thread. Because if you kill a thread, all the intermediate states that were at stake while the state is running can never recover it. Basically, if you kill a thread, you can as well kill the whole process or the whole program. And in Erlang, you can kill a thread because there is no shared state. That's the only reason why you can kill a thread and process it in Erlang. There is no shared state. So if there is any kind of shared state, you can't kill a thread. Unless you have this property. And this property I call observability or PC losering. If you've ever read the great article called PC losering. That's a great article by Alan Bowden on PC losering. And if you have that, you can do all kinds of nifty tricks I will talk about later. Basically, it means that you can start your program, run it, at some point say, hey, stop. And this would be with no side effects, with no visible side effects. And at some point, you can recover the abstract state. And what can you do with the abstract state? Well, for instance, you can do things like implement it with a different implementation. For instance, you can run your program on one machine and recover the abstract state and then run it on a different machine. While it's running, you interrupt the program while it's running, you ship it to another machine. Or you can implement garbage collection this way. I have a labeling from my abstract system is just a graph rewriting system. My concrete system assigns addresses as labels to nodes. And garbage collection will be just reassigning new labels to my nodes. So you can do all kinds of stuff with that, and I will discuss more about the things you can do with that. And so this would be with some implementation 5. And this would be with some implementation 5, for instance.
Another question.
Yes?
Is there significance of black versus green?
Yes! Black means hypothesis, green means conclusion. If I have what's in black, I have what's in green. Very good question. Sorry if I wasn't clear.
And I always forget what it's called. I just want to say it right. What is the apostrophe?
I just mean that it's a different state. It's a different state.
Oh, so it's not prime.
Prime, yes, it's prime. Prime.
What are two apostrophes?
Because I want to make it correspond to this is C prime. I go from C to C prime, which is a different state. I go to C prime prime second, whatever. How do you call it? Second?
Double prime.
Double prime?
Just two prime.
2 prime, okay.
Sometimes you see triple prime, and after
Okay.
that it's meant.
So C double prime and A double prime corresponds to C double prime. There is nothing that corresponds to C prime. You interrupt the prime in the middle, there is nothing that corresponds to it. It's not a safe bond. This is basically generalizing the notion of safe bonds.
And how is C different than C prime in that circumstance?
C is a starting, you start your computation at C. You do plenty of computations. You run your thread, and you interrupt your thread. And then what? You cannot do anything. You can kill it, or you can use restart it. Unless you have PC losering, which is going to recover the abstract state, and you can do everything you want from there.
So it's basically a stopping point in the computation.
Yes. So from stopping the low level, you can reach stopping at the high level.
Okay.
Observability means, and in PC losering it was an operating system called ITS developed at MIT, where you could observe other processes. And when you observe a process, you are guaranteed to never catch it when it's in the middle of the system call. So they said you can never catch another process when it spins down. You always catch it while it's in a valid state for the abstract machine that has everything represented in memory.
So the diagram on the left, are the arrows bidirectional, or is that?
No, it's just association. This means that, okay, I have an abstract system A here, I have a concrete system C here, and I have an implementation there, which I call phi. Okay, last diagram. If you are familiar with category theory, usually people only consider total functions. So here it's partial function, so a partial function is this. A partial function is an arrow from a subset of C into A. So this is a partial function. You can draw it this way. If you have an injection J from O to C, so O is a full subcategory of C if you want, that is between 2 points in O that are also in C that have an image in C. All the arrows that are in C are also in O.
By arrows, you mean like implementation?
Arrows or these.
Okay.
So in a category, you can say I can always compose these arrows, basically. A category is a diagram with nodes and arrows, and if arrows have the same, well, if the end of an arrow is the start of the other arrow, then this arrow exists also. That's a category.
Okay.
So category is basically diagrams with nodes and arrows that respect this compositionality thing. So, that was my previous talk. What time is it?
9:57.
Okay, thank you.
So are you a category theorist?
No,
No.
this is very, very, very basic category.
That makes me feel bad.
Yeah.
Sorry. Okay.
Did you just label the properties?
Yes, this is liveness. Liveness. This is totality. This is soundness. Without soundness, you can throw away your. So let's put it in double. If you don't have that, you don't even have an implementation. So, and this is just partial function or partial function. Partial function.
During your talk, will you be using the whiteboard?
No.
Okay.
And this is just operational function itself.
The meaning of C prime in soundness is different than PC string, right?
The meaning of what, sorry?
The meaning of C prime in
Yeah.
soundness is different than PCL.
PC losering?
Because it would, soundness would imply the PCL string.
Soundness does not imply PCL. PCL ring implies not PCL doesn't imply
Oh,
soundness.
you're right. You're right. I'm sorry. Yes, I'm sorry. Yeah. I missed my meaning. Yes.
And the problem is not only that people don't have PC usuring, is that they have PC usuring at one level but not at the other level. For instance, under this Java implementation, there is PC usuring with respect to garbage collection. Because you can interrupt a thread to do the garbage collection, but there is no PC usuring with respect to your implementation, to your program environment.
Yeah.
So-
So soundness pretty much means that the C prime is actually a state that is a meaningful state.
Look, we suppose that we separate the meaningful state.
Yeah.
Then
Yeah.
the arrow of connection
Right.
is.
Right.
And people who just came, you don't have to care about that. But you missed something, but
No, you killed something in your existing memory. I don't have that.
Oh, okay.
Right.
What's the one under totality? That's a
under totality, I call it
Good, how are you?
Yeah, yesterday.
I call it computer, but let's call it stepability.
Yeah.
What?
Stepability.
Sure.
Stepability?
Yeah.
Hello, Jay, how are you?
Sure. Doing okay. Use my throat a bit much yesterday.
In other topics, I call it completeness, but I think stepability is a better word.
It seems like that's describing
Talking to anyone, wears it out.
almost
Oh, this is.
I don't know, it's like,
It means that
saying you have, if you can get from A to A prime, then you have existence of an algorithm. What, it's like,
maybe.
I don't know. How would you explain it in English?
In other places, I call it completeness also, or completeness. If I can get there, then I call it completeness or stability. Or it means that indeed, anything you can do in the abstract, you can do in the concrete. And if you have both totality and stability, then indeed you are fully a complete. Okay. So what time is it? So is there someone recording, or do I have to wait? Oh, you're recording? Okay, let's start then. Anyone else coming? Okay, let's start. Hi. Is it on? Hi. I'm Francois Rene Rideau, and today I'm going to tell you about computing versus computers, the Hunem point of view. So this talk is based on my blog, Hunem Computing, which is itself based on my old Tunes project, which is some of the finest vaporware never written from the 1990s. My take-home point is that you should think in terms of computing, that is, interactions of which you are part, and not in terms of artifacts, which is like software or hardware devices under you, where you are a god above. I will tell you a lot about orthogonal persistence, which is how I think systems should, a property I think systems should have. And I will tell you about reflective systems and first-class computations, which is how I believe a system should be architected. And my bigger take-home point is that a change in point of view on what computing is will change what software you write. That's the plan of my talk. And let's start with Hunems and Yahoos. So the other day, I was with my friend N, and I wanted to install Overtone. Overtone is a music, interactive music software which is written in Clojure. And Clojure is written Clojure is written in Java, so I had to install the JVM, so Clojure JVM. To interact with Clojure, you need Emacs. Clojure, Overtone uses Super Collider, real-time music system to actually output real-time sounds. And all of it is running on Windows. So I want to install Overtone, and actually I need to install like 6 different pieces of software. Okay. Issue, not only do I have to hunt for all these files online, including configuration files to correctly configure Emacs to run with Clojure, but Clojure and Emacs disagreed on where the home directory was. Emacs was convinced that its home directory was in the local app data thing, and Is it better now? Okay. So Clojure thought that the home directory was the user profile directory, the Windows user profile directory, and Emacs thought that the home directory was the local app data directory, which is obviously different. So we had to figure out why did we change .emacs and it doesn't do anything. And of course, in the end, after we installed all those things, managed to configure Emacs, managed to configure Clojure, everything, it still failed because the supercollider binary distribution was 32-bit and the JVM was 64-bit. So in the end, after half an hour and an hour, we said, stop it, we'll use Linux. Linux was just as hard to make work, but I had managed to make it work before. And the main problem was Pulse Audio versus JACD, sound diamonds, incompatible, etc.
For the people that just come in, would we be able to restart so I can like fix the audio?
Sure, let's restart. That was my first, my first. Kind of. Okay, there's a lot of people. Come in while you can. Thank you. Sorry.
Can you say something real quick?
La 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 la. Okay. Okay. Tell me when you're ready. Okay, ready. Okay. Hi, I'm Francois Rene Rideau, and today I'm going to tell you about computing versus computers, the Huinem point of view. This talk is based on my blog, Huinem Computing, and which is itself based on my old Tunes project, some of the finest vaporware never written from the 1990s. My main point is that you should think in terms of computing, not in terms of computers, in terms of interactions of which you are part, at the same level as humans, and not in terms of software below humans that are just devices and artifacts, hardware or software below us. I will discuss orthogonal persistence, which is a property I think every operating system should have. And I will briefly describe reflective systems and first-class computations, which is how I believe systems should be architected. And my larger point that I want to make is that changing your point of view will change what software you write. That's the plan of my talk also. And let's start with Winams and Yahoos. The other day, I was with my friend N, and I wanted to install Overtone, which is an interactive music system written in Clojure. So I install Overtone, I need to install Clojure, which I need to install Emacs to interact with. I also need to install SuperCollider, which is a real-time music backend, language, etc., development platform of its own. And Clojure runs on the JVM, and everything runs on Windows. So I have to install 5 different systems that run on top of Windows. And of course, it never works. You have to hunt like for files online. I think it's an issue in itself. And Clojure thought that its home was the user profile directory of Windows. Like most people might think your home is that. But at least this version of Emacs was convinced that the home was in local app data. So we could modify the .emacs. It changed nothing until we figured, oh, actually, they disagree as to where the .emacs is. And in the end, it still didn't work because SuperCollider was distributed as a 32-bit installer or something, and the JVM was 64-bit, so it never worked, and we dropped the thing. Of course, in the end, we made it work on Linux, which was a lot of work too, because of the issue with the sound daemon JACD versus Pulse Audio that Ubuntu uses. And it required quite a lot of manual configuration, but in the end, we had something that worked. And if it's not a solution, I think that it was at least a scriptable, reproducible workaround. So my friend N started asking questions like, how do you trust random programs from people you have no relationship with? And how can programs disagree on the home dir or on the ABI? And if they disagree, how come you have to dig through log files to figure out what is happening, being a super advanced programmer, instead of the system telling you, hey, there's an incompatibility there? And why do you need to configure anything at all? Why isn't just there a sane default, you install it, it just works? What is this concept of files? And why do you have to redo everything on every machine? Why are there like 5 different or 6 different development platforms? Why can't you do it with just one? And why do anyone but the developer of any of these items have to worry about anything? Why can't I just be like, I install it, it just works? And you will think, oh, my friend N is pretty ignorant. I mean, how ignorant of how things work. That's how it works. But these questions are not stupid either. And you say, my friend N does not know how computing happens in the human world. And yet, I would argue that my friend N is a computing expert, just not a human expert, a Huinem expert. What are Huinems? You remember this guy, Gulliver? He's a guy who is famous for making lots of travels by sea, and every time he had a shipwreck. So don't travel with this guy. His most famous travel was in the land of Lilliput, very tiny people, and his last travel was in the land of Huinems. And Huinems are the sentient beings that are equines. They look like horses, but don't call them horses. Horses are stupid, dirty, filthy animals that are not sentient. And you wouldn't like to be confused for a Yahoo. And a Yahoo is those stupid, non-sentient, filthy animals that Huinems use as beasts and cattle. So all these stories were told by Jonathan Swift in a book, but don't trust all the details of that book because he used it for social commentary. So so my friend, I called her N because that's simpler. She was a computer scientist in Huinem land, and she had heard, like everyone, the story of this Gulliver, and she didn't believe it because she thought it was just all made up for social commentary. And she decided to prove that this story was totally impossible, and it's impossible to travel by sailing to a land where there were lots of humans. But then she found a flaw in her proof. So being an honest and obsessed computer scientist, she decided to go all the way to the end of this flaw in the proof, and she ended up sailing to our land. And happily for her, she was not as bad a sailor as Gulliver. Unhappily for her, equines are not treated very well in our lands. And then she was enslaved, as most equines are, and she evaded the knacker, where equines that are not docile end up, and she also evaded, even worse, a government research facility, where equines that display any kind of sentience are sent. Happily for her, she was rescued by the French resistance. And that's how she ended up in a barn somewhere connected on IRC, and that's how I met her, and she told me her story, and we became best friends, and now she likes to ask me lots of questions about how humans do computing, because while she's staying with us, she's doing comparative studies in human versus Huinem computing. Okay, some things you need to know about Huinem computing. There is no such thing as magical things for Huinems. They don't have magic powers, they don't have oracles, they don't have anything beyond Turing computability, they don't have quantum computers, they don't have super duper fast computers, they just have basically the same general technology as we do. But one thing they do have that we don't is a point of view in terms of computing, not in terms of computers. Which means that, well, I'll describe in detail what that means, but they have a different point of view in computing, and it's a distinction not about how to write software. Functional programming is just as valid or invalid for Huinems as it is for us, but it's a distinction about what software you will want to write or not to write. In the point of view of computing, computers are means, they are not ends. Dijkstra famously said, computer science is no more about computers than astronomy is about telescopes. And Huinem would agree on that with Dijkstra, except that I believe to Dijkstra, computing was a way to explore pure math. And for Huinems, pure math are very important, but more important than math is meat. That is, computing is a tool to build interactions in which sentient beings are involved, Huinems or humans, assuming humans are sentient. This is something we'll have to skip. Being a Huinem, my friend N had never seen a keyboard because, with whose keyboard, that doesn't work very well. So she's fascinated by me typing on my Space Cadet keyboard, and she watches it for hours, and she has a double screen where she can see what's on my screen and what I'm typing, and then she tells me, there is some kind of magic keycord that you press at every so often, like all the time you press this keycord, and I can't fathom what it's doing because it doesn't have a very visible effect on what you're doing. What do you think this magic keycord is?
Save.
Hmm?
Save.
You've seen my slides? Okay. So it's not the enter key because that's obvious. It's not Control-Del because I don't do it all the time, but it is indeed Control-X, Control-S, which in Emacs is saving the file. And then she asked me, what is this saving files thing? So I have to explain her files. Files are kind of objects, but they are kind of low level because they are specified as a level of bytes. So okay, that's a weird way to specify objects, but okay. And if you don't save a file, then all your changes are lost. And not only that, but you also have to do a daily prayer to backup, the God of data recovery, who is a very merciful God if you do regular prayers, but a very revengeful and merciless God if you don't. So N says, okay. So in what rare and unpredictable events you try to save your thing against? Like, what kind of dangers you save things for? And I say, oh, I can just do a bad click there, and I will lose my stuff, or I can close my app, or my software may crash, or I may have a power loss because my laptop is not plugged in, or the device may malfunction, it may be lost, it may be stolen, it may be broken, it may just die of old age. And my friend N says, oh, but these are not at all unpredictable things. They are like very predictable catastrophes, and the solutions are totally automatable. So why do you save files manually? I say, well, there are historical reasons. Back when I was young, files were big and disks were small, so you couldn't just save the files anytime because otherwise it would run out of disk very fast. And since then, that's how it's always been done. That's all how computer systems are designed. Also, the computer cannot decide when to save a file. If I start to cut a big piece of code here to paste it there, and the system saves it in the middle, I'm hosed. Or if I start to open the parentheses here, and before I close it there with text, the thing is saved, then some other process may see the wrong thing, and everything will be wrong. So I can't let the computer decide that. Also, personally, I've been beaten way too often. I've lost like hours of work not saving things. So now I just Control-X, Control-S. It's hardwired. I don't have to think about it. I don't waste like precious neurons on thinking when should I save my file. I just save it. And every time I have a pause in my thought, boom, Control-X, Control-S. Yes, so I didn't even notice I was doing it until she told me. And then she told me, okay. Actually, you have automated it. You just automated it in wetware. You automated it in your brain, which is totally opposite to the sacred motto of the Guild of Rene programmers, which translated in English is, I object to doing things that computers can do. Indeed, the whole point of computing is to automate the things in the things that works for automation, that is silicon or mechanical devices, and keep the things that cannot be automated in wetware. And sometimes, so the highest goal of computer science is to automate that which can be automated. And sometimes you have to accept defeat. Sometimes things cannot be automated, or it cannot be automated yet, or you don't have the resource to automate it, or it costs too much to automate. That's fine. You have to accept that sometimes you can't automate stuff. That's wisdom, accepting defeat. But when the victory is just at hand, you could just have automated it, and you didn't. And you surrender. That's foolishness. You could just have won, and you lose because you're foolish. That's foolishness. Difference between wisdom and foolishness. So WinM systems have what I called orthogonal persistence. I didn't invent the term. Orthogonal persistence is when everything is just saved by default. I type it, it's saved. You know, you open a window, you type A equals 1, then you wait 5 seconds, you put a hammer, you destroy your computer, you burn it to the ground, you dissolve it in acid, you buy a new computer, you log onto it, and the Windows is still there with A equals 1. That's orthogonal persistence. And the general motto is, if it's not worth saving, it's not worth computing. If I didn't mean for it to stay, I wouldn't have typed it on my computer. I would just have thought about it. Hey, it's just cheaper. If I typed it on my computer, I probably wanted it to remain and to be there. So think about it another way. Who among you spills his registers to cache manually, decide when a register gets spilled to L1 cache, L2 cache, L3 cache, RAM? No, you let the computer do it. You automate it. You don't think about it. Why should you have to manually spill your RAM or virtual RAM to disk? And why should you have to spill your disk to a remote backup manually? It can all be automated. That's so simple to automate. Of course, there are modalities. There's a whole range of possible latencies that you may, and quality of services that you may expect. If you pay a lot and you are connected directly to the internet and you have a stable power supply, then in a few seconds you can have replicas all over the world. If you're on a laptop at a conference disconnected in the middle of nowhere, you will not expect to have replicas immediately, and maybe to save power, you will only save stuff to disk every minute. But so there is a whole range of latencies that cannot be predicted in advance by the programmer or by anyone else than the end user. Space. There is enough space for anything you type. Maybe when I was a kid, there wasn't, because computers had a few kilobytes of memory, and recording everything you type was, for a few minutes, would have taken kilobytes of memory. But today, we have like terabytes of memory. There's no reason why any key you type should ever be lost, unless you want it to be lost. And you can even record everything you view on your computer. And maybe you don't want to record 4 kilopixels per second, no, 50 times per second. But you just need to store the small state from which this is computed. Oh, it's just displaying the game Pac-Man, and this guy did this and that. And there are a finite number of events that matter, those where you input stuff, and everything else is predictable, or should be. And then that's the only thing you need to log in your persistence log. Everything else can be recomputed from that. So if you have a system that has strict determinism and can replay from a small state, then you don't need to record every frame, and yet you can replay every frame. So you only need to keep high-level events and discard everything that's irrelevant and store those high-level events in the persistence log. There are also issues of privacy. Most of us want our persistence log to be private to ourselves. We want to share something with other people. Some things require triple encryption because that's where I store my bank accounts. But other things only require simple encryption. Or maybe not, I don't know. You choose. But the important point is that the programmer cannot know that. The programmer cannot know in advance whether the program will run on a laptop, a palm top, a desktop, a grid. He cannot know what are the latency preferences of the end user, how much money he's willing to put on making things persistent with what trade-offs. So in the end, it's the end user who has to decide, because the programmer can't. And the end user can, of course, delegate things to his expert programmer who works for him. But the programmer of the program who does not work for him cannot know and cannot make good choices for him. So in an orthogonally persistent system, you will want to have a notion of domains of persistence, where the programmer can say, hey, this is my work, it's important. This is my play, it's important. This is my porn, I don't want to share it. This is my bank account, they need to be triple protected. This is where I conspire against the government or against my wife. You want to have separate domains for the different things you do. You want probably the windows to be in different color, and you want to have something that prevents you from copy-pasting from one domain to the other without triple-checking what's happening. All these things. But once you have these domains, which are not defined by the guy who writes the program that runs the domain, but defined by the user, once you have these domains, you can hook some of the domains that matters to worldwide storage providers. For instance, your bank accounts and Bitcoin, whatever, you want them to be super encrypted and replicated 10 times over with an N2M scheme. I need N of them to know the answer out of M, so I can get the memory back. But you can have all kinds of wild schemes differently for a different domain of persistence. And the data that you store this way has no reason to ever be lost until the end of serialization itself. There's no reason why the data you write should be lost. Another design principle is that the end user who knows his needs is the one who must be able to specify what he wants. And the programmer who does have no clue whatsoever what the end user will want should not be forced to specify anything about it because he has no clue. So each can specify what they know, no need to specify what they don't. In Yahoo systems, sorry, my friend N tends to call our systems Yahoo systems. You have fractal transients. Maybe some modern app will save configuration for you without you ever pressing the save button. That's a great innovation in the last 10 years. Woohoo! But underneath, it's all transients at every level. Even these apps don't save over the cloud or don't share. They don't have a notion of domain of persistence. When you log in from another device, will have different preferences. Or some preferences will be shared, others won't. It's a big mess. The programmers have to deal with very complex protocols for serializing, saving, transacting, upgrading, converting. It's horrible at every level, except maybe in a very superficial and brittle way for the end users. Of course, the end programmers can't handle the configurations that matter to the end users because they have no clue who the end users are and what are their needs. And the end users, who is ultimately responsible for his own safety and his own welfare, he's responsible for it, but he has no tools because all the software is closed for him and he cannot do anything. So we have fractal transients at every level. Everything is broken, snafu. What's snafu already? Situation normal, all fucked up. And I call that a disaster of Homeric proportion. You may think that the joke is on me for compulsively typing Ctrl-X, Ctrl-S. Yes, the joke is on me. But the joke is on N and everyone else. My friend Anne, since she was rescued, she was typing using Microsoft Paint to draw these weird Huinem symbols to writing system. I don't understand it. And she had written probably the greatest epic ever written by Huinems in ages because she had been through so much stuff, like being enslaved, traveling to foreign lands, discovering foreign computers. She had been through so much. She had written some heartfelt thing. To me, it's just winning. It's like, oh. But to Huinem, I'm sure it was the greatest epic ever, and it's all lost because he never clicked on save. He just write, erase, write, erase, write, erase, and never saves. She just assumes that you can always go back in time as in any decent system. But no. But it's just not my friend N. How many Homeric sagas have been lost because people don't save or forgot to save or forgot to make a backup or had to spend hours and hours writing stupid systems that save things for you? Like, maybe thousands of man-years have been wasted. Maybe millions of man-years have been wasted because systems don't have orthogonal persistence. And this is despite the fact that OIML had orthogonal persistence in 1978, I think. It's a German system. You should read about it by Jochen Ditka, the guy who wrote L3 and L4. Okay. So some perks of orthogonal persistence besides persistence itself. You never lose a session to a crash. How many of you have opened too many tabs and had their browser crash and then had to cry and then install a browser extension to remember your tabs? How many? Raise your hands. Okay. Sure, but, well. So not just your tab, not just the URL of your tab, but all your session state can be preserved by orthogonal persistence. So you never lose data. Also, you have infinite redo and undo. Sometimes you do something and you want to undo it. And in most apps, you can't undo. In some apps, you have undo to 1, 2, 3, 10 levels, or maybe up to a fixed size buffer of 1 megabyte of activities, something. And it's very, very, very difficult for the programmer to get that right. Lots of effort, and yet very little return on investment for all these efforts. But with orthogonal persistence, you have eternal instant replay. Oh, I did something. I can go back in time and just replay it. By definition, everything is instant replayable. So if you have your Facebook feed or the Huinem equivalent, and Facebook starts to display something you want, you click on it, and then the item below you like it too, but it's too late to have clicked. You go back in time, and Facebook displays you something else. Well, too bad for you. You'll have to dig through it to find what it was. But in an orthogonally persistent system, it's there. You can just go back. People can never undo things under your feet. If someone deletes your comment or deletes a comment they wrote, but you ever saw it, maybe they did it on their computers, but they can't delete it on your computer. Everything you saw belongs to you. You can search it. You can analyze it. It's the opposite of Yahoo systems, where everything you do belongs to your credit card processor who knows more about you than you do. So, yes, data belongs to the user and not to someone else. I see someone here who is very happy. One disadvantage of orthogonal persistence is deletion is costly. Indeed, when everything is basically a persistent log, if you want to undo something, oh, I typed my password there, or I gave up some secret information, how do I delete it? Well, if you really want to delete it, you can, but then you have to rewrite all the logs since then. You have to do an Orwellian retcon thing where you retroactively, and that's an evil thing, and you have to better be very trustful of your system to write new logs correctly. You better test the thing a lot. It requires a lot of testing. It's an irreversible operation. You better be sure what you're doing. And of course, you would never delete other people's copy when you do it. You would only delete your copy, not the NSS copy. But on the other hand, if all you care is not see this thing, like this was very bad porn, or this is like a friend I want to forget, you can just de-index them. You never see them again. They won't appear in your thing, and that's cheap. De-indexing is free, or it's just, but deleting, real deletion is very costly, and it should be. So in orthogonally persistent system, the primitives are not mutable records, they are immutable facts. Perks for programmers. At least 30% less code. There was an old IBM study that said at the time 30% of the code was just to deal with serialization, deserialization, saving, restoring, and that was not even counting any advanced error recovery. Just basic saving, restoring, communicating the things. And so all these can disappear. 30% less work for everyone here, except those who, of course, implement orthogonal persistence, as this guy there. So one thing is, in an orthogonally persistent system, there is no save primitive. Everything is saved. Of course it's saved. You don't have to save it. There is never a save instruction. Instead, there is don't save primitive. When I'm going to display this high-resolution pictures at 60 frames per second, I will tell the system, hey, you know what? Don't save that. Put it in a domain that's not actually persisted because it doesn't matter. So there is no save primitive. There is a don't save primitive. And another perk for programmer, you can experiment without fear. Oh, what happens if I run this program that I just downloaded from the internet? Oh, it does rm-rm/. Oh, no big deal. Go back in time. You can experiment without fear. Also, all bugs are 100% reproducible by default. If you do a very low-level program and you insist on hitting the hardware, or if your hardware has a bug, the hardware itself has a bug, or your kernel, if something very low level has a bug, it might not be 100% reproducible. But if you write above the normal layers of abstraction, then yes, of course, it's reproducible. Duh. Everything is deterministic. It's reproducible. I have a bug. I can reproduce it. I can debug it. No problem. Last thing is that you will think in terms of abstractions, not of bits. In a Yahoo system, you think in terms of files that are sequence of bytes that are themselves sequences of bits. And everything in the end is bits. The only common interface between two different programs is bits. Sure, while you write into your programming language, you write using objects, integers, whatever, but as soon as you have anything that persists and anything that's important persists, you have to deal with bits. In a Rene system, you deal with your abstractions, not with your bits. So you don't implement from the bottom. When the way that Yahoos do programming and metaprogramming, they have to specify everything from the bottom. And there I also look at this guy because I think he gets it wrong. From the bottom means that you have to care about a common abstraction to all your end users. You have to assume, well, all the end users will have is Windows 7, or all they will have is Linux with a kernel 3. Whatever. And I cannot really trust them to have anything above that. So I will have to specify my software as this big pile of abstraction from this bottom to the place where I want to be. And Yahoos have meta-programs, but most meta-programs for Yahoos are things that are just at compile time. Like meta-programming is just like generative programming. And sometimes they have some runtime stuff, but it's horrible, very low-level kludges, and you're guaranteed to break things if you use them. And in practice, Yahoos only use it for debugging. Like you can use ptrace, or you can use a kill, or things like that on processes. Like it's a tool just for system administrators and programmers who do debugging. It's not a tool for everyday programming because it's so fragile. And the last thing about Yahoo programming, metaprogramming, is all the abstractions are leaky. When you write a program, it's written in C or in Lisp or whatever, or in Haskell, and suddenly you drop down to something underneath, and your program breaks because you have a space in your file name, or your program breaks because you parse a URL, and suddenly there's magic code that runs code on your computer and takes over. So all your abstractions are very brittle and leaky, and basically you can never be sure of anything. Rene metaprogramming and programming is done at as high level as possible, but no higher. No higher is very easy because you try to write a program, you see I want to go beneath the abstraction, I can't. So the program will tell you when you're at too high a level of abstraction. So not higher. And then every program you can write on top of its own DSL. And the metaprogram is whatever is underneath that DSL and implements it at compile time, but also at runtime. And very importantly, WinAIMs have full abstraction. Full abstraction is the idea that a program can never see what's underneath. There is the magic, the veil is rigid. You cannot see the man behind the curtain. You cannot, at least the program cannot see the man behind the curtain. You cannot see the turtles under you. The program is fully isolated by the layers underneath. Very important, like if you have to remember anything, any one thing from this thing, these slides, is that full abstraction is super important. Of course, your program can explicitly allow some non-determinism. You can say, hey, this program, I don't really care whether you evaluate arguments from left to right or right to left. Here I want, give me any file. It will give you a file. Or give me any integer, it will give you an integer. And as long as you say, I don't care, then you don't care. If you lie, that's your problem. But the system is allowed to do the things that you say you don't care if it does, and is not allowed to do things that you don't say you don't care if it does. So once you have full abstraction, you can do something very cool called program migrations. Those who missed the thing I did before, that's okay. I have another talk from Boston Haskell last week that you can consult. So program migration is basically when you change the underlying metaprogram under the program while it's running without restarting. The obvious thing is when I run some program on my phone and I decide it's too slow, let's run it on my laptop. And then I decide it's still too slow, let's run it on my desktop or on the cloud. And you don't have to stop it. You just say, hey, just migrate there. And this is possible because there is full abstraction. Therefore, it doesn't matter if your program is currently compiled for ARM. I can recover the abstract state, and this abstract state I can transfer to x86, and there's no problem there, or from x86 to whatever the cloud provider is running. But it's not just for changing the CPU underneath. You can also change things like I/O devices. You can say, this program is currently connected to this sound output or this console output, and I want to rewrite it, rewire it. I can do that while the program is running. Hey, program, you're not running on this screen or this window. You're running on that window. Your persistence policy, your speed, latency, robustness policies, your optimization levels, everything can be a matter of choosing the metaprogram underneath. And you can also do tricks like, hey, every time I type A, there's a bug. So when I type A, I will trigger omniscient debugging or time travel debugging, depending on how you call it, same thing. And I type A, now I enable a low-level type travel debugging, and then I can see what happened and explain exactly what happened. You can also think of garbage collection as migrating the object graph. Garbage collection is a matter of having a programming language that conceptually does graph rewriting. And when you do graph rewriting, you don't care at what address a particular node is. All you care is that in the abstract, it's a graph. And then your graph in memory is represented as some nodes that are at our given addresses, and garbage collection is just migrating your node representation from one representation to the other. But the abstract node remains the same. And when you have this notion that you can change the metaprogram under a program without restarting, a lot of things can be simply implemented that way that are very, very difficult to implement if you don't have full abstraction. And I know people who do that at a very low level, but what I want is to do that at a high level. And when you have all these features, everything is different in a WinAIM system than in a Yahoo system. There is no impermanence. You never have to care whether your things are saved or not. They are saved. You still have to clean up discipline. You still have to care to not store your 4K pixels 50 times per second in your store, or you will pay a big bill in storage fees. You don't have to worry about bysequences, but you have to still to worry about object boundaries. if I want to share this part with, who do I want to share this object with, or this part of the object with, what persistent policies do I want at what boundaries. You still have to think about object boundaries. You don't say files, but you still have to worry about which version of the file do I want other people to see, which version of my program do I want to be compiled. Certainly not the one with an intermediate state, but some of them are, you still have to think about release management. I don't have to worry about file names because everything is saved, but I still need to worry about data indexing. I still have to worry about better way to find the data than remembering, oh, I did that on Tuesday at 4 a.m., so let's scroll back then. You don't have to worry about startup scripts because the system never starts more than once. It just is. But you still have to worry about configurations and differences. Oh, this guy has a cool thing on his machine. I want to replicate it. Can we identify the meaningful diff between the two that will make his cool features appear on my machine? You don't have to worry about finite access rights like Unix or WX crap, but you still have to worry about access capabilities that are relevant to whatever domain you're implementing. So the common point is you don't have to worry about the low-level mechanisms anymore. Yahoo systems that are focused on the devices and the software and the things and the capabilities of those things, and you build on top of that. In the Winem approach, you first focus on the abstract things that you care about. You really care about which data you want to save and which you don't want to save, who you want to share it with or not. You care about the abstract interaction that you have with the data and with other people. That's what you care about. And then you take care of that. So it's a different approach. You approach things from the top instead of from the bottom. What happens if you have bad memories? Since everything is persistent, what happens if I make a mistake so serious that the entire system is garbled and forever? I do an out-of-memory error. I do a fork bomb. I have a deep meta bug where the compiler is so hosed that the code that it generates for system calls or something very basic is wrong, and I can't restore it. What happens if I garbled my store and the code that stores data is itself corrupted and stores zeros or random strings instead of the actual data? Well, the first answer is try not to do that. It's bad. What happens if I have a bug in GCC or a bug in my Linux kernel or a bug in some device driver? That's bad. Yeah, yes, bad things happen. Try not to do them. And since they do happen, even if you try not to do them, you better keep all snapshots. You better keep your backup. You better have regular drills for backup and restoration, because a backup that you never restore is as good as nothing. And you should make sure that you don't do anything that's irrelevant for your needs and that can only introduce bugs. The less you do, the better. And you use watchdogs to automate things for you. And automating things for you is possible in a Winem system because there is this top-down view of the system knows what it's doing. Whereas in a low-level Linux or Windows or Yahoo system, trying to do a backup has so many ins and outs. Since the system does not know what you want to do, it never knows what it has to back up or restore, and it requires a lot of configuration that is different for everyone, and there is no solution, no general solution to backup in a Yahoo system. There's a funny story that Winems tell each other from the bad old days. So in the 80s, there was this system in East Germany, Eumel, that had orthogonal persistence, and once in a while someone would do something that would host the total system. But since at that time computer was very slow and disks were slow, and they were using floppy disks for persistence, if you can believe that.
I'm sorry, did you say East Germany?
East Germany, Eumel. Jochen Litkopf was from East Germany, so far as I can tell. So sometimes someone would host a system, like very bad, deep bug, and what they would do is that they would turn the power off. And then all the other users would be angry, like everything I did in the last 5 minutes was lost. Okay, but at least I didn't destroy the system where everything would be lost forever. The problem with that is that since the 80s, the latencies have dropped to 5 seconds, from 5 minutes to 5 seconds to 5 milliseconds, then you need to be very fast to pull the same trick. So you can't use that trick. So if you can't use that trick, what you do instead is you escape to the meta system. What is the meta system? If you've ever used an old 8-bit console like an Apple II or any 8-bit console, at some point you can either hit a reset button or Control-C or Control something, and you are dropped into the monitor. It's a very simple system. All it can do is things like pick and poke and call and inspect memory, things like very simple things. But you can do everything. From these simple things, you can do everything. So in a reflective architecture, you drop into this monitor that has a small reserved part in memory, and then you can merge back the system log up to the point where you think it's still safe. And then you can try to identify and try to restore from a safe point in the past and drop or put aside the logs, the changes that you don't want. What happens if there's a bug while you're debugging? You're in the monitor, so you've used that reserved memory, and now there's a bug. And are you done? No, because the first thing you do with this monitor is to virtualize itself. So you have a small bit of physical memory that's reserved, but as soon as you have a lot of virtual memory that's reserved, you can use that virtual memory to virtualize the monitor, and then you can debug the system, but if there's a bug while debugging the system, you can still virtualize that and start over. And then you can use dichotomy to find where exactly the catastrophe happened and undo it. So really scary bugs happen, and you can't always avoid all of them, but you can eliminate entire classes of them. You can just prove correctness of some bits of your system or test it like SQLite does. If you haven't seen the SQLite test suite, it's mind-boggling. But there is one advantage that, well, you can already do that with Yahoo systems. So what's the advantage there? Well, the advantage is that in a WinM system, most programs don't touch persistence. It's only very low-level programs like the equivalent of their kernel and their compiler that really matter for persistence. Everything else can just assume the persistence to happen. So deep persistence bugs can only happen with a very small attack surface. And that very small attack surface you can prove correct or test like crazy. And that's something you can't do for Yahoo. For Yahoo, since you implement everything from the operating system up, every program by definition can corrupt your file system and do anything. There's no way to avoid it unless you do a lot of virtualization and sandboxing, etc., and then your programs don't work the way they should, and it's actually not a Yahoo system anymore. So either you're going all the way to the WinM system, eventually I hope they'll do it, or you remain Yahoo and things don't work. Of course, the real fallback for WinMs and Yahoos alike is just to keep and test your old backups. There's no way around that. You can make you may make that cheaper and the likeliness of having to use it lower, but in the end, you still have to have backups. One thing that's interesting is that virtualization is just like branching. You can imagine that your entire system is just like a Git system where everything, every keystroke, everything you do, but at a high level, is recorded in the system. And when you virtualize something and decide to only keep things up to that point and then diverge, it's just the same as branching in Git. Then undoing a very bad bug is just like rebasing in Git. It's like the Orwellian rewriting history. Of course, there are things you can't undo, like you can't unprint your data if you started printing like 10,000 pages of garbage, or if you launched a few missiles, it's hard to undo. Maybe you can pay reparations to the guy, declare peace. No, we didn't intend to destroy your plane. Something can't be undone, but that's not specific to WinM systems. That's specific to computing in general. So you still don't want to do the bad things, but at least the bad things you do inside your system can be undone and easily. And once again, as far as virtualization goes, what matters is not hardware acceleration. I mean, it's good to have hardware acceleration, but what you really need to have virtualization is full abstraction. If you have full abstraction, you are guaranteed that replaying the log will be faithful, will do the same thing or something equivalent the second time around as it did the first time around. If you don't have full abstraction, anything goes. You can save all the events. That doesn't guarantee that you will retrieve the system you had. So full abstraction is once again the big thing. It means the higher levels can't see the implementation specifics and the essential difference between Yahoo and WinM systems. And it's not a property of your hardware. It's not a property of your language. It's a property of your system. And to a WinM, a leaky abstraction is not just a top priority bug. They happen. Sometimes you really make a deep bug in your kernel or something. Leaky abstractions happen. But when they happen, it's not a top priority bug. It's a security issue. And if you see someone trying to break abstraction in your system, you call the cops on them. And unless they are penetration testers that you paid for, you should get them in jail forever. So a first-class computing system is what you end up if you take full abstraction seriously. First-class computing system means that you don't have just full abstraction for one level. There's the system and there's the things underneath. Instead, you consider that every program that anyone wants to compute is its own computation, its own computing system. And it's not just a programming language. It's a programming language plus the runtime execution state. It's not the static semantics of your system. It's the dynamic operational semantics of your running program. When I change the meta program under a running program, I care what was the running state. I don't want to just restart the program with an empty state and reset it. I want to preserve the current state and do something else with it. So this notion of the program with its running state at the level of abstraction that I care for, not at the level of abstraction of bits and x86 instructions, but at the level of abstraction that I care for, that's what I want to preserve. And then I can move it from x86 to ARM or whatever. But it's because the system has a first-class notion of computation where it knows what program I care for at what level of abstraction. So every program is its own computing system, and then you realize there's not a one true global computing system. Most Yahoo systems has this notion that there's a one global computing system and you do all your side effects in it. You have a big shared file system for everyone, you have a big shared whatever for everyone. For WinM, it's just if you only have global variables. At some level of your system, you only have global variables. That's obviously stupid. You want to have local variables, you want to have scoping, you want to have a system where you can locally do something, it will be isolated, and you are the one in control of what happens where and what interactions are visible by whom. So I have a talk about first-class computing systems there. I gave it at Boston Haskell last week. This is a short URL. I hope the video will be online soon. And it's having not rigid tower. So in Yahoo system, you have this rigid tower from the common level up to your program. And all that is your deliverable. You deliver a binary that has all that. In a WinM system, instead, you deliver stackable modules. You deliver just this abstract computation. And you can, doesn't matter what's underneath, actually you can change what's underneath at runtime. So obviously I'm not going to deliver a binary that has everything that's underneath. I deliver a computation that has just something, just this top level part, so the part that I care about. And then you can restack them and change them. And so Yahoos have operating systems where they have a privileged kernel that does everything and you build on top of that. Instead, WinMs have dynamically relinking of meta programs. If I want to talk to a sound card, I will not talk to a sound daemon that then talks to the kernel that then talks to the sound card. If I want to talk to a sound card, I talk to the sound card directly. I bleed directly into its memory. Why is it correct? It is correct because at compile time and link time, I make sure that I'm only using trusted functional programs or whatever that will not do out-of-memory errors or out of bounds or anything. I have full abstraction. I can trust my compiler to do the right thing. Therefore, I don't need anyone between me and the sound card. Unless I explicitly want to share the sound card with someone else, so I still need a protocol for sharing. But I don't need a kernel at runtime between me and my resources. Quality instrument software. Persistence, robustness, security, blah, blah, blah. Yahoo programmers often dismiss them as non-functional requirements because they think, oh, the program should do this, so these are the scenarios, and the rest is just like stuff we can add on later. Like we can add security later, or we can add robustness later, or we can add persistence later. And unhappily, everything, what they add, it can never be robust, it's horrible, it never works. And to WinMs, these are not non-functional requirements, because the requirement is not to have an artifact. It's not what is easy for the artifact, and first the artifact must do this, and then it must have some other properties. The artifact doesn't matter. What matters to a WinM is the interaction, and the artifact is just a means to this interaction. And persistence, robustness, security are not features of the interaction. They are not features of the artifact, but they are features of the interaction, and they are part of the functional requirements of this interaction. So you have a very different approach, and that leads to a very different outcome. And trying to make your artifact easy at the expense of your interaction is basically sacrificing the ends to the means. Making it easier to write programs so you don't have to worry about persistence is absurd. Throttling down. So you can think of a runtime metaprogramming architecture like WinMs have as, in terms of turtles. You have your program that you care about, and underneath are turtles. So you care about some level of your programs, and you don't really care what turtles are there. But sometimes you do care. You want to debug, or you want to add some properties to your program. So you pop up the turtle. You pop up some turtles, and then you can let the system change as it wants the turtles underneath, and you can decide exactly at which level of turtles you want to care about. And you can change that dynamically, which means that in WinM systems, as opposed to Yahoo systems, you don't just build up, you build down. In a Yahoo system, you take components, you compose them. Composing, we're in a functional programming conference, we like to compose stuff. We start from things and we build stuff on top. But it's very important to build up, but the thing that we never do or we fail to do is building down. Building down is having an existing program and changing the implementation underneath, changing something underneath, and popping these turtles up and changing the turtle and popping the turtle back down. Things like that. And that's what Yahoos can do, and that's what WinMs can do. And neither libraries nor servers will allow you to do that. It's not something that you can retroactively fit or emulate in a Yahoo system. The only way to have it is to have your WinM system and your system designed as a WinM system. There is no kernel. There are lots of things. So WinMs don't have kernels. They directly talk to the hardware, etc. For something like access control, they transfer the ownership of the sound card, for instance. So do you want to handle the sound card? Here it is to you. Now it's yours. And maybe your metaprogram itself will revoke your access and give this property to someone else. But all I know is I'm writing some sound, and this sound will compile to whatever banging bits in whatever sound card there is or not. And actually, if I'm not talking to a sound card, it can be all compiled to a NOP and accelerated. Yes, the sound is off. I'm not even generating the sound because the sound is off. There is no apps. If you have something that has essentially one-way communication between the user and the program, then it's not an app, it's a document. For instance, a game is essentially a document. You explore the game. Of course, when you can scroll down, you can export different parts of the document, but it's still a document, it's one-way communication. If there's both-way communication, if the user is contributing to the thing, then it's still a document. It's a document, but then you're editing it. So what you have is a document editing platform, something like Emacs, just less antiquated. And Yahoos don't have to re-implement their widgets, because you can just say, hey, I want a file, give me a file, and your metaprogram will give you a file. And that will be all for everyone. So 1 minute only. OK, so it's better division of labor because specialists will deal with the widgets. And instead of having 100 apps which each have a bad widget, you have like 3 widget implementers in the whole world. And just like in Emacs, you have the correct widget installed, and the document developers don't have to deal with it. OK, you can see how do we get there? There are lots of technical and social problems. Don't worry. Metaprogramming is programming, and you can already do that. The main thing that's missing to have a WinM system is the vision and the will to make it happen. There is a nice misquote of Saint-Exupéry. If you want to build a ship, don't drum up the men to gather wood, divide the work, and give orders. Instead, teach them to yearn for the vast and endless sea. The goal is not the system. The goal is a saner approach to computing, and you can already do it today and every day. Main home points: think in terms of computing, not computers. Value orthogonal persistence. Use reflective systems. And yes, it would be great if you condense the vaporware into actual software, but what I bring today is not just vaporware. It's not definitely not software, but it's something else. It's wetware. It's changing the point of view about computing in your minds. Thank you.